Okay, welcome to a presentation. This presentation is on introduction of determinants. We need determinants to continue with our concepts like cross products, and we also need determinants for solving systems of linear equations. So you'll see that the way I introduce determinants here, I'll basically start with a problem, a situation which involves a system of linear equation, and I'm going to start very small. Linear equations, two linear equations with two unknowns, two equations and the two unknowns. That's how we're going to start. Is it clear what we're going to do? So from that, we have to, by the end of this presentation, we have to know exactly what we mean by determinant of a matrix. And this is not any matrix, but a square matrix. Did you get that clear? Okay. So let's start this way. A simple problem involving square matrices is following. Let's suppose we have two types of pencils, let's say colored pencils and the ordinary pencils. And let's suppose also we've got like two school-going kids, let's say here child number 1 and then child number 2. Now, if these two kids have got need these two types of pencils, let's just suppose that the first child there needs two of the colored pencils and the second child needs three of the colored pencils. The ordinary pencils, let's say this one, the first child needs 3 and the second child needs 1. All together? Okay. And then, obviously, if these two people go for shopping, leaving home, they don't know the price. What's the price? But for sure, where they're going to buy, they're going to have a price list. They're going to have a price list. The price list maybe will be reading colored pencils, so much in cents or rands, and the ordinary pencils, so much in cents or rands. That's clear, isn't it? Okay. Now, if we're to make a shopping statement in terms of what this child will spend, obviously, if she buys 2 colored pencils, she will spend 2 times X. That is clear. Cannot be easier than that. Is that fine? Yeah. Then she would also spend for ordinary pencils, 3 of them. Then she will spend 3 times Y. Do you agree? And then let's suppose then here, what happens here, this child ends up spending about 13, could be 13 rands or 13 cents, or not interested in the units, we just say in quantities there. Okay? And then this one will spend 3 times X for colored pencils plus Y for ordinary pencils. So then, and you find that this one is spent 9. That is what we have now is system of linear equations. In this case, we've got this equation and that equation. And then this, we can change this system of linear equation and we can change it to any equation. Just listen to me. I'm talking about 2 equations, but I'm saying we can change the equations to any equation. Now it's one equation. What equation? What we can call matrix equation. Because now, if we look only at the coefficients on the left-hand side here, if we only focus on the coefficients, we're talking about 2 and 3, 3 and 1. And we can put this as a package like that, which we call a square matrix of 2 by 2. And then here, what we have there on the right hand side, we also have got this x, y, which symbol represents what? The price list. And then on the other side, on the right hand side, then we've got 13 and what? And 9, which represent the totals which these two people spent. And then at the end of the day, we've got three entities here. 1, 2, 3. We've got A, which we can call the matrix of the coefficients. 3, 1. That's the matrix of coefficients. And then we've got this matrix here, we've got X here. You'll see the reason why I'm calling it X soon. This is little x and little y. And that we can call the matrix of the unknowns, because these are the costs which we haven't determined. Is that right? So it's a matrix of the unknowns. And then we have B here, which we can call, which have 13 and 9. And then what we have here, we've got the matrix of independent terms. Now, if we look at this situation here, you will see that this is a situation which is exactly similar to a situation which is 2x equals 8. A known entity, a matrix, multiplied by an unknown equals to a right-hand side which is known. And then what we have here, actually, we have something like A, x an unknown, that's the reason why I call it x, equals to B, a known matrix. So in other words, now, we are like looking at a practically grade 1 simple equation, but we're looking at it in a different situation where coefficients are not numbers but matrices. This is the same equation which you could look at and say this is 2 box equals 8. Now, what do we do there? What do we do? Check this thing. To solve this equation, listen very carefully. To solve this equation, what did we do? With an equation 2x, I'm talking about the experience we've been doing for many years. We've been taking 2x equals to 8. To solve it, we would normally multiply it by, which is the same as, do you agree? Okay. But you see here, this is division. And you take a note, in matrices, we never talk of division of matrices. Altogether? Okay. But as this is division, we can talk it, leave the word division and say we multiply it by an inverted 2. Because when you take 2 as a rational number is 2 over 1. And when we're dividing here, it's just as good as multiplying by 1 over 2. Altogether? Which means this is the same, this 1 over 2 is the same as 2 to the power minus 1. And actually here what we do, we would say that we are pre-multiplying 2 by 2 to the power minus 1. We are pre-multiplying 8 by 2 to the power minus 1. Altogether? Okay. Now the idea is, this is an equation. This equation is an equation whereby we don't know x and we don't know y. So we want to take these ideas and see whether we can use them here to solve this equation. So if we were to get such a kind of a situation, which means we would need a matrix like this, which plays the role of this, which when you multiply this by 2, we get 1. And you remember 1 is an identity for multiplication. Do you agree with me? When you multiply by 1, the answer is the same number multiplying. Now it leaves the number identical as it was. Then we say 1 is an identity for multiplication. Do you agree? So then here, then we'd have this multiplied by that. Then we'd get something here which behaves like 1. And actually this will be the identity matrix. I hope you understand what I mean there. By the identity, basically I mean it's a matrix which would multiply any other matrix and leave it as it is. Out well? Okay. So for 2 by 2, identity is also a square. We'll call it I sub 2, meaning an identity square 2 by 2. Is simply a matrix with a 1, 0, 0, and a 1. If what we're talking about, the vectors, is still very close with you, you remember that this vector E1 was what? 1, 0. And we said it was a unit vector. And the E2 was a vector 0, 1. It's also a unit vector. So actually the identity matrix now is basically a pack made of what? Of E1 and the E2, which gives us exactly what we see here as the identity matrix. That's not a problem, is it? Okay. So now what would happen now if this happens like this? What would happen? We would then multiply in this equation. In this equation, let's get a new slide here. In this equation, AX equals to B. Having a matrix here which multiplies A whichever way, this way, and they give us an identity. If we have such a matrix, what would you do here? We'll simply multiply here and multiply there, and pre-multiply here. What would then happen here? This would give us then the identity here. This would give the identity here. Then we have an identity multiplied by X, then equals to A times B. And you remember now what we said about multiplication is that this is a 2 by 2 matrix, and this one is a 2 by 1. And if these two numbers here, like we can see, they're equal, it would mean that we can multiply these matrices. But only if we can multiply these matrices this way, the answer will also be a 2 by 1. Meaning the answer we're going to get here is simply going to be a B1 multiplied by, a B1 and a B2. So that it has got how many rows? 2 rows and 1 column. 2 rows and 1 column. And here again, the identity will be 2 by 2, and the X is 2 by 1. So when you multiply there, that will leave X as it is. What is X? X is a 2-component column vector or column matrix, which is like this. And then this will be equal to what? That will be equal to what? To B1 and the B2, and that, then what done? Then here we should simply say now, therefore X is equals to B1, and the Y is equals to B2, because that is what that will be defining what the equality of matrices. When do we say matrices are equal? When corresponding entries are equal. Okay, that's the thing. So now, what is the task now? The task is, if given A, let's say given A, square matrix, how so given A, that's the question. How can we get A inverse? Altogether. Now, all what we're going to discuss now, from now onwards, we want to make sense. For example, now we're starting with the simplest matrix of 2 by 2. We want to make sense that given a matrix of 2 by 2, how can you get an inverse? Now, let's say we're given A. In this case, I'll get my A to be A, B, C, D. Let's say we're given that. And then we're wondering now, what is A inverse? And then the only thing we can do is to speculate and say, let's suppose the inverse was UV P Q. At this moment, listen guys, A, B, C, D, we know. It could be given values 3, 4, 5 altogether. But we don't want to pick particular values, then we're not working in general, then it defeats our idea. I want to work in general and say what is going to happen altogether. Okay. So what we're going to do, what we know is that if we multiply A by its inverse, we're going to get the identity. And the identity in this case is 1, 0, 0, 1. Everybody's in agreement with that, isn't it? Okay. So what do we do? We perform this. What do we do? We perform that. So we're going to say A inverse equals A, B, C, D, U, V, P equals to 1, 0, 0, 1. That's what I will invite you now to write two systems of equations given this. If you do the multiplication, you can get two systems of equations given this. Can you try to do that? Okay, let's do it together to maybe help those who are a little bit forgotten about multiplication of matrices. This is how we do it. Check. We're going to take this column, transpose it. Transpose means take a column to be a row to be a column. So this is a column. We're going to make it a row. So we're going to have here U and a V. Once we've made it a row, then this U is going to come and multiply here, multiply there, and V is going to run along that column. And as we run multiplying there, we add. So we're going to have here A U plus B V, C U plus D V. That's the first column of that matrix. The first column here multiply to make a first column. And then we go to the second column, do the same thing, If we transpose here, we're going to have P, Q. I'm just putting it underneath here so that I have space. No? They're not going to do. We're going to run up along the columns. Then we're going to have AP plus BQ. And we're going to have CP plus what? DQ. And then we close here. And then we have 1, 0, 0, 1. That's clear so far, isn't it? Then immediately when we there, we appeal to the equality of matrices. Equality of matrices. We say they're equal if corresponding elements are equal. So what do you hear? This element here is in row 1, first column. So this is 1, 1. And this is also 1, 1. So we're going to have here AU plus BV equals to 1. Then we're going to have CU plus CU plus DV. CU plus DV equals to 0. That's one system. Equation 1, equation 2. And then on the other hand, we're going to have AP plus BQ equals to 0. Then we're going to have CP plus DQ equals to 1. Don't lose sight of what we're looking for. We're looking for U, V, P, and Q. And that is going to give us the nature of this kind of entity. We're together, né? Okay. Then we go this way. Let's take this one first and solve this one. We're going to use the simplest method we know, which we call the method of elimination. You know it, isn't it? We eliminate one variable, we solve the equation. We eliminate the other variable, we solve the equation. You know that one. So now what we're going to do now, we're going to write this thing as this way, as AU plus BV equals to 1, CU plus dv equals to 0. Then we put a line here and get a line there. And then let's say this is equation 1 and this is equation 2. Now, choose which one do you want to eliminate. Let's eliminate u first of all, isn't it? Let's eliminate u first of all. Now, to eliminate u, first of all, these two coefficients must be equal, but they must differ by the sign. So we have to find numbers to multiply here and multiply there, make them equal and differ by the signs. This is what we're going to do. Just check what we're going to do here. We're going to do the following. We want to eliminate u. So we are going to say we're going to multiply by minus c here and by multiply by a here. So then what we're going to do, just check what we're going to do. We are going to leave the first equation as it is, as au plus b v equals to 1. And then when we multiply here, we're going to have minus ac here plus ac. Then we're going to have a 0 here. Altogether, when we add the two equations. And then here we're going to have what? We're going to have minus bc here and the ad here. We're going to have minus bc and the ad. And we're adding these things algebraically. We end up with what? With ad minus bc, and that will be the coefficient of what? Of v. Do you agree with me? My sister, we're multiplying here. Check what we did here. First of all, we multiply there, we got ACU. And we get here minus ACU. And here we get what? ACU. Plus, we get a 0. Then when we come here, what are we going to get here? We're going to have minus BCV. And here we're going to have minus ADV plus ADV. We add algebraically, we get AD minus BV. Altogether. Then when we come to the right hand side here, we simply multiply this by minus c and this by 0. We just remain with the minus c. Do you agree? Okay. And then when you do that, you can see that in this last equation here, this is your equation 1 and this is your equation 2. How did you get this equation 2? You got it by multiplying minus c times equation 1 plus a times equation 2. Where? Here. But this equation immediately gives you what? An answer to your v. It says v is equal to minus c over ad minus bc. Altogether. Please get convinced that that is what you get. Do you see how we got that v? Okay. Now let's come to the next thing now. Now we can eliminate v and then we can know our u. The good thing about v now, check what is good thing about v now. V is written in terms of the matrix A, whose entries we know. Altogether. Okay. There's nothing which you don't know here. It's all the things we know we got from matrix A. So when we come here and eliminate v, in the here we're eliminating u, and here we say eliminate v. Let's eliminate v. We're going to have, I'm going to use exactly the same equation here. What I'm going to do, we're going to have, we have got equation 1 and equation 2. I'll keep the equation 1 as it is. I'll put it here as a what? AU plus BV equals 1. In equation 2, we want to eliminate V. We want to eliminate what? V. We are going to multiply the first equation by D, and the second equation by minus B. Check what's going to happen now. Check what's going to happen here. I'm going to have here BdV, here minus BdV, 0. Do you agree with me? Then at the top there, I'm going to have ADU minus BCU. So U is a common factor, isn't it? Then I'm going to have here AD minus BC brackets U equals to, on the right hand side of the system, we're going to have D multiplying there plus minus 0B, which is what? D. So get this as D. And then conclusion, U is a D over what? AD minus BC. Just look at the beauty. The denominator is the same. All together. The beautiful thing about this thing is that the denominator is the same. So then, let's move on. Let's now come to this one. Let's come to this one. Then let's call this equation 1. Let's call this equation 2. What are we looking for now here? We're looking for P and Q, isn't it? We're looking for P and Q. Let's do exactly the same thing. Let's eliminate Q. Decide to eliminate Q now. Let's eliminate Q first and get P. Let's eliminate Q and get P. What I'm going to do here, I'm going to multiply. We're eliminating Q, is it? We're eliminating Q, is it? I want to get here D multiplied by minus B. Check that. Let's write our result somewhere here. What are we going to do then? We take the first equation as it is, as AP plus BQ equals to 0. Do you agree? And then when we come now, we multiply these two and add to get a new equation at the bottom here. We're going to have here DBQ. Here we're going to have minus DBQ. Add to 0. And when we come this side, we're going to have ADP minus BCP equals to minus B. What are we saying here? We're saying therefore P is equal to minus P over AD minus BC. Do you agree? Again, P is given in terms of the matrix we know. So there's nothing new. And then conclusion, now we come to the next one. The next one, we're going to write the same equation again as AP plus BQ equals to 0. And then we want now to eliminate Q. What we're going to do now, this is a D and this is a B. So the first equation needs to be multiplied by if this one needs to multiply by B, saying we multiply by minus B, and the other one we multiply by D. We're eliminating this one, isn't it? Are we eliminating Q or P? Oh, sorry, we're eliminating P. We've already got Q. We've already got P. Now we should eliminate P to get Q. So we don't want this now here. We want to eliminate here. So what we're going to do here, we're going to multiply the first equation by minus C and this one by A. And now here we're going to have minus ACP plus ACP 0. Then there we're going to have BC minus BC and AD, which means AD minus BC, cry if you don't see it, minus BC times Q equals to what? 0 there plus A, which is equals to A, which then says therefore Q is equals to A over AD minus BC. Please don't worry about this. Nobody's going to ask you to do this thing. I'm just doing it for you so that you understand at the end where does this thing which got from comes from. Is it? Okay. So that is the thing. So first thing first, the denominator is common. Did you see that the common? So we have a common denominator. And something so common deserves a name. Guys, when you get something and it's outstanding on its own, it deserves a name. And then I'm saying call AD minus BC the determinant of A equals to A, what was matrix space? It was A, B, C, D. That was the matrix. So we call this determinant of A. Notation is very important. We say det A to say denote determinant of A. We can also use this like absolute value. We just write A, B, C, D. Now, if you check what it is there, it's AD, which is like AD. And this is like a line which you call the principal diagonal. Principal diagonal. Minus BC. And then here we've got the secondary diagonal. So the determinant what it is basically the product of the principal diagonal minus the product of the entries on the second diagonal. Then we've got a determinant of a 2 by 2 matrix. All together. Now let's come back and check what it is here. Now give me something. Tell me something. Let's look at these four values. V, U, P, and Q. Would have a problem sometimes there. When are we going to have a problem with V, P, and Q? There is a condition for V, P, and Q. Otherwise, this thing we're talking about, the inverse, is not going to make sense. What is the problem? Okay, the problem is if AD, BC is equal to 0, then this entity is not defined, this entity is not defined, this entity is not defined, this is not then the matrix, the inverse matrix is not defined. So for a matrix to have an inverse, we're simply saying the determinant must not equal to 0. And when the determinant is 0, we say the matrix is singular. If the determinant, if AD minus BC equals to 0, then A is singular. These are terms which you must know if you are doing mathematics, right? Singular. Otherwise, A is non-singular. Am I making sense so far? Am I making sense so far? Okay. So there it is. So what we do now, the simplest thing we can do now is now to organize and see how our inverse look like in terms of the given matrix. Are we there? Okay, these are our results from our calculations. Where did we start from? We started from A, being equals to A, B, C, D. And we assumed, we said, let's say A inverse is equals to what? Is equals to U, V, P, Q. But now what we've got? We've got now A given, all these given in terms of the entries here. So what we have now, we've got a big matrix this way now. What we have in U, we've got D over the determinant AD minus BC. In V, what we have at V, we have got minus C over the determinant. I'm just repeating this word because I want you to learn it. We've just learned it today, isn't it? What did you have at P? At P, you've got minus B over the determinant. And here we've got A over the determinant. You can just go a little bit backwards to vectors. We said if you've got a vector like A, which is 2, 1, which is, of course, we can look at this vector as a column matrix. If we look at it as a matrix, we can just give it a name. Let's say A prime, and we can look at this as 2, 1 as a matrix of 2 rows and 1 column. So vectors are not very far away from matrices. We can look at vectors as matrices of some sort. That's what I'm saying. So now we said, if we've got a vector like this, if we talk of 2, let me not say 2, let's just say lambda. If we talk of lambda A, never mind what lambda is, it's as long as a real number, we can now talk of a vector which is 2 lambda and a lambda. What do you mean there? We mean that if you multiply a vector, the number just goes inside and multiply. So if you see a common factor in the entries of vector, you can actually also take out a common factor lambda and leave 2, 1. Altogether, this is what we're going to do here. Taking this as a vector, we can do the same thing. Taking that as a vector, we can do the same thing. Taking this as a matrix, we can do the same thing. Then we come up with what here? 1 over AD minus BC multiplied by D minus B minus C A. Okay. Now, at this point now, we can say basically we've got a formula for getting an inverse of a given matrix. This here will be A inverse given A, which is that. It's just playing around, guys. What is this thing now? If you look at what's happening from here to there, it's just playing around. The only thing you need to know is to calculate the determinant. Okay, we've already said how to calculate the determinant. You're given A is that. This is A. Want the determinant, you just put bars around it or use the word det of A. Then you calculate as principal diagonal AD minus B altogether. And then after that, you rearrange these entries like this. You will simply get your inverse altogether. Now, let's say at this point, let's say we have achieved 2 things. 1, inverse of a 2 by 2 matrix, and strongly, message is very, very strongly, inverses are only designed for square matrices, nothing else. Altogether, determinant is only for square matrices, nothing else. That's the important thing. So 1. So we might like to find out the inverse of 2 by 2 matrices. But before that, we've also achieved what? We've also achieved what? What's the next thing we've achieved here? To compute the determinant of a 2 by 2 matrix. These are 2 things we've done here. We've managed to know what is an inverse. We've managed to so that to get an inverse, we need a determinant. We now know what is a determinant. So at this point, guys, let's say stop here and say thank you for listening. The next presentation will then do a lot of things you can do with inverse of matrix, and even find an easier way of finding the inverse of a matrix, which you can extend to 3 by 3, 4 by 4, and so on altogether. Okay, at this point, thank you for listening. My name is Charles Wasfan.